All right, good morning, ladies and gentlemen. Today we're going to go over Calc Review 11. There's only one problem, and it dealt again with sort of analyzing graphs like we've been doing the past few days. So let's jump into it. Again, with these problems, it's really important to understand exactly what information you're given. Here we're given the graph of f, and we're told that some other function g is defined in this way. So g of x is this definite integral of f. So this means that we're going to need area under curve, right? Because a definite integral graphically means that we're finding the area under the curve of whatever function we are integrating. And so I've gone ahead and I've just kind of filled out all of the areas under these triangles. All in the positive sense, because the negative integral value depends on what direction we're heading. So is dx positive? Is dx negative? Is the height of are the heights of the rectangles positive? Are they negative? So we'll take that into account once we get to it. All right. So part A: does this function have a relative min, a relative max, or neither at x equals 10? All right, so first of all, in general, relative extrema, the candidates for relative extrema are only your critical points. So that's the only thing we have to worry about in general when we're finding relative extrema. And once we do find those candidates, we use the first or second derivative test to determine min, max, neither. Now in this case, they actually tell us to focus on a certain point. So there's no real need to find all the other critical points right now. So we're just going to focus on x equals 10. All right. And if g of x, so the question is there a minimum, maximum, or neither at x equals 10 on the function g? All right. So in order to take this point and determine if it's a min, max, or neither, we need to find the derivative of g to use the first derivative test. Well, if g of x is defined to be this integral, then fundamental theorem of calculus part 2 tells us that the derivative of g, or g prime, is just simply going to be equal to f of x. And just again, the proof of that is because the antiderivative of f, the definite integral of f from 2 to x is equal to big F of x minus big F of 2. And when we differentiate big F of x, we get little f of x. When we differentiate big F of 2, we get 0, right? So it makes sense to say that the derivative of g is just simply equal to f of x. All right, moving on. The first derivative test. So the way I set it up is I draw this number line. This is the value I'm analyzing. And above here, I'm going to sort of analyze g prime, or in other words, I'm going to analyze f of x on the left of this point and to the right of this point. So notice you'll see I put a negative and a negative here. I obtain that knowledge from looking up at the graph. This is the graph of f, and I see that f is negative just to the left of 10, and f is negative just to the right of 10. So that means g prime is negative on either side. And so to finish up, we say that since g prime of x is negative on both sides of 10, this is neither a minimum nor a maximum on g of x. All right, that's that. Part B: does the graph of g have a point of inflection at x equals 4? Justify your answer. All right, folks, justify your answer means you do need to make some sort of an explanation for your claim. So you can't just say yes, no, maybe. You need to justify your answer with some kind of a statement. Now, I've actually recreated, this is the graph of f. So notice I've actually just taken this portion here and I brought it down here. So when we're talking inflection points, we can either discuss the second derivative. Does the second derivative change from positive to negative or vice versa? Or does the first derivative go from increasing to decreasing or vice versa? So again, I've taken the graph of f, which is, as we know, this is g prime of x, right? So if I want to find the second derivative of g, or g double prime, what I would do is I would take the derivative of f, or I would find the slope of the graph of f. So you can see that from 2 to 4, the slope is 2. And that another way of saying that in this situation is that f prime of x is equal to 2. Similarly, from 4 to 6, the slope is negative 2. Another way of saying that is that f prime of x is equal to negative 2. So over here, that's equivalent to saying that g double prime is 2 on this interval from 2 to 4, and g double prime is negative 2 on the interval from 4 to 6. So I can argue that g double prime changes from positive to negative on this interval, on either side of 4. And so I might claim that there is an inflection point of g at x equals 4 since g double prime changes from positive to negative. Actually, I should add at this point. So that's one way of arguing this problem, showing all this work and then making your claim based off the work that you just showed. Alternatively, you can actually just make an explicit argument for what you explicitly see. It's totally fine to say that there is an inflection point of g at x equals 4 since g prime changes from increasing to decreasing. So I can make my argument in terms of just simply the derivative of g, which is f. And we can see here that f from 2 to 4 is increasing, and then from 4 to 6 is decreasing, right? So your argument, either one of these arguments is fine. Just make sure you're showing your work for any one of them. And I should add at this point. Okay. Part C says, find the absolute minimum value and the absolute maximum value of g on this interval. Notice it's a closed interval, and then of course we have to justify our answer. So part A deals with a relative extrema, part B deals with absolute extrema. The major difference is there are now more candidates in play for absolute extrema. So the candidates are your endpoints as well as your critical points. All right, so the first thing I did was I set up this table, and -4 and 12 were the first values that I plugged in because they're simply the endpoints. And then I got to work on determining the critical points. So that is, when is g prime of x equal to 0, or when is g prime of x undefined? And it turns out that g prime of x is never undefined. G prime of x is equal to f of x, and you can see that f of x is continuous. So I don't have to worry about that, right, for this particular problem. But what I do need to do is determine when is f of x equal to 0. Well, going up to the graph, we can see that f of x equals 0 at x equals -2, at x equals 2, at x equals 6, and at x equals 10. So that's a lot of candidates. But we can be wise about this and right off the bat, omit 2 and 10. Now, why can we omit 2 and 10? Well, first of all, in part A, we've determined that at x equals 10, g of x has neither a minimum or a maximum. So because we can see that the derivative is negative and negative on either side. Similarly, for x equals 2, the derivative, or the graph of f, is positive on either side. So for x equals 2, there's neither going to be a min nor a max on g. So we can actually ignore those points, those critical points. But we cannot ignore -2 and 6 because those are both candidates for, those are both relative max/min. And so they're candidate for absolute max/min. All right, so now what we need to do is determine the values for g of these functions. Now we are told that g of x is equal to the integral from 2 to x of f of t dt. So x equals 2 is sort of like the forced starting point, and realistically, or typically when we find the value of a function like g by integrating a rate, we do so by taking some starting point and then adding to it this integral, which of course, remember, represents the net change in this case, g, right? Because f is really g prime of x. So the thing is, in this situation, g of 2 is just equal to 0, right? So if you integrate g of 2, it's getting a little messy, but let me just show this side work. G of 2, by definition, is the integral from 2 to 2 of f of t dt, which is equal to 0. So I just want you to be aware that we are still using this fundamental truth of starting point plus net change, but it just so happens that the starting point is the y value starting point is equal to 0. All right. So anyway, for the net change, what we need to do is determine the area under the curve. So for this first integral, we're determining the area under the curve from 2 to 4. 2 to -4. So let's go up to the graph. We are started at 2. That is our anchor point for all of these integrals. And we're going from 2 all the way to -4. Notice that the direction we're heading is from right to left. So our dx's are going to be negative. So this first set of areas that you see here, this 4 here, there's a positive height but a negative width. So this is actually a -4. Same thing, this next area is a -4. So in total, we're at -8. And now this area that's below the curve is actually going to be considered positive because we have a negative width and a negative height. So we have a -4, a -4, and a +4 for overall a -4. So the value of g of -4 is just -4. G of -2 is -8, a very similar argument. G of 6, so now we're integrating from 2 to 6, which means our dx's are now positive. So if the heights are positive, then the areas will be positive. If the heights are negative, then the areas will be negative. G of 6 ends up being 8, and G of 12 ends up being -4. Now the question asks for the absolute max or min. We've found the value of G for each of the candidates, and as you can clearly see, the absolute maximum value of G is 8. The absolute minimum value of G is -8. And so just make sure to make that statement. Always tie sort of your answer in a knot, tie a little bow on it, and make a final statement. All right. And as far as the justification, all of this work that you did prior, that is your justification. All right. Part D, let's just read through it quick. For this entire interval, find the intervals for which g of x is less than or equal to 0. Now, in this situation, notice it doesn't say to justify or anything. So really, all you need to do is determine when the value of g is less than or equal to 0. All right, and just reminding that g of x is defined to be this integral. And we want to know when is it negative. Actually, we want to know when is it negative or 0. All right, so since we're anchored at 2, we're starting at 2. I know that when I travel from 2 to the left, anything above the x-axis will result in a negative area under the curve. So from 2 to negative 2, G is negative. And then as we go from -2 to -4, the areas start becoming less negative. Like we start adding area because we are going left and we have negative heights. So that area becomes positive. However, we never add enough area to overcome as the amount of negative we've already put into the mix. So we go from -8, an area of -8, to an area of -4. So all the way from 2 to -4, this area, I'm gonna do inclusive here because from the interval from -4 to 2, the area is either negative or 0. Similarly, okay, now when we move to the right of 2, we have a +8 from 2 to 6. And then we have an accumulated area of 0 overall from 2 to 10 because we've added 8, but then from 6 to 10, we've subtracted 8. So right now we're back to 0 at 10. So I should put an inclusive bracket here. And then from 10 to 12, we are obtaining a -4. So the area turns negative right at 10, right after 10, all the way up through and including 12. And there you have it. That's your final answer. Again, there was no justification necessary. So as long as you came up with the interval, you were good to go. All right, ladies and gentlemen, that's all for today. Hope all is well. Hope this helped. We will talk tomorrow. And I'll actually be posting some updates and stuff today. So check out the Google Classroom stream. All right, take care. Bye.